any soil when depositing contains some voids in them. The property of the soil which permits the water or any liquid to flow through its voids is called permeability. Permeability is the ease with which water can flow through the soils. There are numerous methods through which we can measure the permeability of a soil in the field or of a representative sample in the laboratory. In the laboratory, we employ two methods. One is constant head permeability method and another one is falling head or variable head permeability method. These tests measure the amount of water that goes through a soil sample in a fixed time interval. Constant head method is suitable for large grained soils which are relatively more pervious because of their larger voids, while variable head is more suitable for small grained soils which are relatively less pervious because of their poorly connected void structure. We have already discussed constant head permeability method. Now let's understand the falling head or variable head method. We perform this test for fine grained soils where quantity of discharge of liquid through them is very small. For this test, we use an instrument which consists of a cylindrical mold. We measure its internal diameter and determine its internal area, which we say capital A. This mold is attached with two filter discs at the top and the bottom. These discs are porous and highly permeable. These are also provided with inlet and outlet facilities. Inlet is fitted with a graduated vertical standpipe. The diameter of this pipe is known and let's say it is small letter d. Also its area is small letter a. We can perform this experiment on both disturbed and undisturbed soil samples. We fill the mold with our sample soil and compact it to a density which may be representative of the field conditions. Or for an undisturbed sample, we take out a soil sample from the ground and trim it to the dimensions similar to that of the mold. We place this sample inside the mold between porous discs. Some space will be left between the mold and the specimen that we will fill with some impervious material such as cement slurry. We fill the standpipe with water and before beginning the experiment, we allow the water to flow through the soil and let it get fully saturated. Even after that, we let the water to flow out for some time so that a steady flow can be attained. A steady flow is the one in which the quantity of liquid flowing per second through any section is constant. Then we close the knob at the outlet and stop the water flow. We refill the standpipe up to a certain height. The height of the water column in the standpipe represents the head or the energy of the water. We assume there is a negligible head loss due to porous disc and the energy of the liquid starts dropping when it begins to flow through the soil. So, if there is a manometer at the beginning of the soil, its water level should be the same as that of the pipe because they are displaying the same water head. Hence, we can think this inlet pipe as the head measurer at the beginning of the flow and we can ignore the first manometer. Now, if we have a manometer at the bottom of the sample and when water flows through the soil, the water level in the manometer will display the exit head of the water. But if we place the instrument in a tub-like container full of water, its exit head will become constant. Also, if we consider the exit head or water level of the container as the datum, then datum head is 0, so exit head is also 0, and initial head of the water level in the standpipe from the datum is, say, H1. Hydraulic gradient, which is the difference of inlet and outlet head divided by the length of the soil specimen in which the flow takes place, will only depend on the height of the water column in the standpipe as outlet head is 0. When we open outlet knob, water comes out and overflow the container. we start a stopwatch and place a graduated jar to collect the overflow water. We collect the water for a fixed time interval t and note down the amount of water collected as capital Q. We close the knob and also note down the final head in the standpipe, which is also the final head difference from the datum. We call it H2. Keep in mind that H1 and H2 are the heights of the water column in the standpipe and also the head differences which are causing the flow. Now, for this system, we may apply Darcy's law, which states that the velocity of flow of a liquid between 2 points in the soil is directly proportional to the hydraulic gradient applied to it. K is added as the proportionality constant, which is called coefficient of permeability of soil. We also write the law for discharge rate as this. We can notice the hydraulic gradient through the soil is changing every instant, as the water head is continuously changing in the standpipe. So let at any instant of time, when the water head was between H1 and H2, the head difference which was causing the flow through the soil is H. For a very short interval of time, dt, head in the standpipe drops by dh height. At that instant, when the head is h, the flow rate can be given as this. And the amount of water collected in the jar with this rate in a small time interval dt will be q into dt. So, using the continuity equation, we can write volume of water dropped or decreased, negative sign for the decrease, in the standpipe is equal to the discharge of water collected or increased in the jar through the outlet. Volume of water dropped in the standpipe is area of standpipe multiplied by the height of drop of water, and the amount of water collected in the jar is discharge rate multiplied by the time interval. We can write a discharge rate by Darcy's law as this. Hydraulic gradient I for that instant of time is h by L. We rearrange it and write it as this. Here, these values are constant, and for our taken test conditions, permeability is also constant. Only variables here are head difference and time. So we can integrate both from the head difference at initial head difference of h1 at time t equal to 0 to the final head difference of h2 at time t equal to t. Now we can integrate and apply the limits, also rearrange to find the value of permeability as this. Here, log has its base e that can also be written as this for base n. In this equation, we have measured and recorded all the required values to calculate and know the permeability of the soil sample. According to the Indian standards, we report the permeability values at temperature 27 degrees Celsius. So if we measure the temperature of the water as T degrees Celsius, then using this formula, we can calculate the permeability at 27 degrees Celsius. Here, K27 and KT are the permeability of the soil at 27 degrees Celsius and at test temperature T degrees Celsius respectively. Mu27 and Mu-T are the coefficient of viscosity at temperature 27 degrees Celsius and test temperature T degrees Celsius respectively. Write down daily learnings or express your creative self in Eels handmade diaries. Buy them at Professor O or Amazon. Link is in the description. Take a look at an example of the following head test of permeability on the Eels website and also read the test on the elementaryengineeringlibrary.com. Link can be found in the description. Thank you.